Welcome back to Sleepy Tinfoil Hat. Settle into wherever you are tonight. Let your shoulders drop. Let your breath find its slower rhythm. Because we are going to spend the next several hours walking together through one of the strangest and most genuinely puzzling concepts that human thought has ever produced. Infinity. The word itself carries a kind of hush, doesn't it? We use it casually in everyday speech, often without really considering what we are saying. We talk about infinite possibilities, infinite love, infinite patience, as if infinity were just a poetic flourish meaning very large or beyond measure. But infinity, when you actually examine it carefully, is far stranger than any casual usage suggests. And the questions it raises touch some of the deepest mysteries in mathematics, physics, philosophy, and the nature of existence itself. Tonight we are going to walk slowly through these mysteries, and the careful contemplation of them is, I think, one of the most genuinely interesting things a thinking person can do with a quiet evening. Before we go further, I want to ask a small favor. If you find this kind of slow, careful exploration helpful for falling asleep, or if some part of your mind genuinely enjoys thinking about the deep questions of existence, while the rest of you drifts toward unconsciousness, please consider subscribing to Sleepy Tinfoil Hat. The channel grows when listeners signal that they are here, and the algorithm is the only way new people find their way to this kind of patient nighttime thinking. And if you would, leave a quiet note in the comments telling me where in the world you are tonight. The country, the city, the hour on your clock if you want to share it. I read these. There is something genuinely moving about watching the slowly forming map of where this audience is scattered, all of us awake or trying not to be at the same hour, listening to the same voice across many different time zones and many different lives. So tell me where you are, and then settle deeper, because the journey from here will be long and patient, and I think worth taking carefully. Now let me begin where most discussions of infinity begin, which is with the basic question of what infinity actually is. The intuitive answer is something like this. Infinity is what you get when you keep going forever, when something never ends, when you cannot reach the end, no matter how long you continue. This intuitive definition captures something important about infinity, but it also obscures the genuine strangeness of the concept, because infinity is not really a number in the ordinary sense. You cannot count to it. You cannot reach it through any finite process. It is not the largest number, because there is no largest number. It is something else. Something that operates differently from ordinary numbers, something that has properties that finite quantities simply do not have. The history of human thought about infinity is itself fascinating. The ancient Greeks were deeply troubled by the concept and developed elaborate philosophical frameworks to handle the problems it raised. The philosopher Zeno of Elea formulated a series of paradoxes designed to show that infinity produced contradictions that should make us doubt our ordinary understanding of motion and change. His most famous paradox involves the runner who needs to cross a stadium. Before reaching the far side, the runner must first cross half the distance. Before reaching that midpoint, the runner must cross half of half. Before reaching that quarter point, half of half of half. The runner faces an infinite sequence of subdivisions before reaching the destination, and Zeno argued that this should make motion impossible, since one cannot complete an infinite series of tasks in a finite time. The paradox seems silly when you first encounter it, because we obviously can cross stadiums, but the underlying philosophical puzzle is genuinely difficult, and mathematicians and philosophers spent more than 2,000 years working out adequate responses to it. Aristotle, responding to Zeno and other thinkers who had been wrestling with infinity, proposed a distinction that would shape Western thought about the concept for nearly 2,000 years. He distinguished between what he called potential infinity and actual infinity. Potential infinity is the kind of infinity that exists when a process can continue without limit, even though at any given moment only a finite portion of the process has been completed. The natural numbers in this view are potentially infinite. You can always add one more to whatever number you have reached, but at any specific moment, you have only counted a finite quantity. Actual infinity, by contrast, would be a completed infinite quantity, an infinite collection considered as a whole rather than as an ongoing process. Aristotle argued that potential infinity was philosophically respectable, but that actual infinity led to contradictions and should be rejected. This view, with various modifications, dominated Western thought about infinity through the medieval period and into the early modern era. The mathematical revolution that finally tamed actual infinity, or at least made it tractable to systematic analysis, occurred in the late 19th century, primarily through the work of a German mathematician named Georg Cantor. Cantor's work transformed the understanding of infinity in ways that continue to be philosophically and mathematically significant today, more than 100 years after his original publications. He showed that actual infinity could be analyzed mathematically, that there were different sizes of infinity, and that the structure of these different infinities had specific properties that could be precisely described. His work was controversial when it first appeared. Many mathematicians and philosophers attacked it as confused or even insane. Cantor himself struggled with periods of severe mental illness, and some of his contemporaries attributed his ideas to his mental difficulties rather than to any genuine insight. But over the course of decades, his work gradually came to be accepted as a fundamental contribution to mathematics, and the framework he developed remains the basis for how mathematicians think about infinity today. What Cantor showed, in essence, is that infinity is not a single thing. There are different infinities, and some are larger than others. The infinity of the natural numbers, the infinity you encounter when you start counting 1, 2, 3, and continue without end, is the smallest kind of infinity. Cantor called it Aleph null. There is also the infinity of the real numbers, which includes all the natural numbers, plus all the fractions, plus all the irrational numbers, like pi, and the square root of 2. This second infinity is genuinely larger than the first, in a precise mathematical sense, even though both are infinite. There is no way to put the natural numbers into a one-to-one correspondence with the real numbers, no matter how clever your counting scheme. The real numbers exceed the natural numbers in cardinality, even though both collections continue without end. This finding alone is genuinely strange when you sit with it. Most people, when they think about infinity, imagine that all infinities are essentially the same. The intuition is that if you have an infinite quantity of one thing and an infinite quantity of another, the two must be in some sense equivalent, since both are unending. Cantor showed that this intuition is wrong. There are different sizes of infinity, with strict mathematical relationships between them. Some infinities are larger than others, in ways that can be precisely demonstrated. The mathematical universe contains an entire hierarchy of infinities, with each level larger than the one below it, extending upward in a sequence that itself never ends. I want to give you a sense of how Cantor demonstrated these results, because the proof is one of the most elegant arguments in the history of mathematics, and following it is itself a kind of meditation on the strangeness of infinity. Imagine that you wanted to show that the real numbers between 0 and 1 cannot be put into one-to-one correspondence with the natural numbers. The task seems impossible to even formulate clearly, since both collections are infinite. But Cantor's argument proceeds as follows. Suppose, for the sake of argument, that you could put the real numbers between 0 and 1 into a list, with the first real number paired with the natural number 1, the second paired with 2, the third paired with 3, and so on through the entire infinite sequence of natural numbers. The real numbers in your hypothetical list would each be expressed as decimal expansions, with digits after the decimal point extending infinitely. Now, Cantor showed how to construct a new real number that cannot appear anywhere in your list. You construct this new number by choosing its digits according to a specific rule. Its first digit is different from the first digit of the first number on your list. Its second digit is different from the second digit of the second number on your list. Its third digit is different from the third digit of the third number on your list. You continue this pattern indefinitely, with each digit of your new number being chosen to differ from the corresponding digit of the corresponding number on the list. The result is a real number that cannot appear anywhere on your list, because it differs from each listed number in at least one digit position. Therefore, your list, however constructed, must have missed at least one real number. This means there can be no exhaustive list of the real numbers in correspondence with the natural numbers, which means the real numbers form a larger infinity than the natural numbers. The argument is breathtaking when you actually follow it, and it has consequences that extend throughout mathematics. There is not just one infinity, but many. The infinities can be precisely compared with each other. Some are strictly larger than others. The mathematical universe contains structures that are genuinely infinite and that have specific properties that finite structures cannot have. The casual identification of infinity with very large quantity completely fails to capture what infinity actually is. Infinity is something different in kind from ordinary quantity, with its own logic and its own structure, and the structure has been worked out in considerable detail by mathematicians since Cantor's original work. Tonight, across the parts that follow, I want to walk you through more of the strangeness that infinity introduces into mathematics, physics, and philosophy. We will look at the various paradoxes that infinity produces, including some that are still genuinely troubling. We will examine how infinity appears in physics, including in the strange infinities that emerge from various physical theories. We will consider what infinity means for our understanding of the universe as a whole, including the question of whether the universe itself is infinite or finite. We will think about how infinity has been understood across various religious and philosophical traditions, with the divine being often associated with infinite qualities in ways that connect to the mathematical concepts. We will explore the deep philosophical puzzles that infinity continues to raise, including questions about the nature of mathematical truth and the relationship between mathematics and reality. And we will sit with the genuine strangeness of contemplating quantities and processes that exceed any finite limit, in ways that the human mind was probably not designed to handle, but that we have nonetheless managed to develop tools for thinking about. What I am not going to do is try to make infinity feel comfortable or familiar. Infinity is not familiar. It is strange in ways that resist our ordinary intuitions, and the appropriate response to it is not to domesticate it, but to acknowledge its strangeness while developing the tools needed to think about it with some precision. The careful contemplation of infinity is, I think, one of the genuinely valuable activities available to a thinking creature, partly because it reveals how much of what we think we understand turns out to be more limited than we typically recognize, and partly because the contemplation itself produces a kind of mental expansion that does not occur in any other domain of thought. The thing I want you to hold in your mind as we begin this journey together is that you live in a universe where infinity may or may not be a literal feature of reality, but where infinity is definitely a feature of the mathematical structures that we use to describe reality. Whether the actual physical universe contains genuine infinities or only very large finite quantities is one of the unresolved questions in fundamental physics. But the mathematical concepts we have developed for thinking about infinity have proven to be extraordinarily powerful for describing many aspects of the world, and the relationship between mathematical infinity and physical reality is one of the genuinely deep puzzles that we will spend our hours contemplating tonight. Lower the lights if you have not already. Let your awareness soften. The concept we are about to explore is older than civilization, in the sense that something like a sense of unboundedness has probably been part of human thought as long as humans have been thinking. But the precise mathematical and philosophical analysis of infinity is much more recent, with most of what we will discuss having been worked out in the past 2 centuries. We are about to spend a long, quiet evening with one of the strangest concepts the human mind has ever produced, and the contemplation of it is itself a kind of communion with the limits and possibilities of human thought. Let me take you now into one of the most genuinely disturbing puzzles that infinity produces, a puzzle that has occupied mathematicians and philosophers for more than 100 years, and that retains its capacity to unsettle anyone who thinks about it carefully. The puzzle is sometimes called Hilbert's Hotel, after the German mathematician David Hilbert, who developed it as a way of illustrating the strange properties of infinite collections. The hotel is a thought experiment, but it leads directly into deep mathematical territory, and the strangeness it reveals is genuine rather than merely apparent. Imagine a hotel with infinitely many rooms, numbered 1, 2, 3, and so on through all the natural numbers. The hotel is special in that it has a room for every natural number, with no upper limit on the room numbers. One night, the hotel is completely full. Every room is occupied by a guest. A new traveler arrives at the front desk asking for a room. In an ordinary hotel with a finite number of rooms, this situation would require turning the new traveler away. The hotel is full. There is no space available. But Hilbert's Hotel, with its infinite rooms, can accommodate the new arrival without difficulty. The hotel manager simply asks every existing guest to move to the room with a number 1 higher than their current room. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. The guest in room 3 moves to room 4. Every guest moves to the next room up. After this shifting, room 1 is empty and available for the new traveler, while every original guest still has a room. The hotel was full, but it could still accommodate one more guest by rearranging its existing occupants. This is already strange enough to require some sitting with. A finite hotel that is full cannot accommodate additional guests, but an infinite hotel that is full can accommodate any finite number of additional guests, simply by shifting the existing occupants down the line. The property of being full means something different in infinite contexts than it does in finite ones. The full, infinite hotel still has, in some sense, room for more, because the very nature of infinity allows for this kind of accommodation. But the strangeness gets much deeper. Suppose now that an infinite bus arrives at Hilbert's Hotel, carrying infinitely many new travelers, each numbered 1, 2, 3, and so on. The hotel is already full, with every room occupied. Can the hotel accommodate this infinite influx of new arrivals? Surprisingly, yes, And the technique is genuinely clever. The hotel manager asks every existing guest to move to the room with a number twice their current room number. The guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6. Every original guest moves to the room with double their original number. After this rearrangement, all the even-numbered rooms are occupied by the original guests, while all the odd-numbered rooms are empty. The new travelers from the infinite bus can then be assigned to the odd-numbered rooms, with the first new arrival going to room 1, the second to room 3, the third to room 5, and so on. Every original guest still has a room, every new arrival has a room, and the hotel that was completely full has accommodated infinitely many additional occupants. This is, when you really think about it, a deeply strange property. A finite collection that is full cannot have additional items added to it without removing some of the existing items. An infinite collection that is full can have additional items added to it indefinitely, simply by rearranging the existing items. The very meaning of full is different in infinite contexts. Infinity does not behave like ordinary large quantity. It has its own logic, and the logic violates intuitions that work perfectly well for finite quantities. The strangeness continues. Suppose instead that infinitely many infinite buses arrive at Hilbert's hotel, each containing infinitely many travelers. So now the hotel needs to accommodate not just one infinite bus full of new arrivals, but an infinite number of such buses, with each bus containing its own infinity of travelers. The total number of new arrivals is, in some sense, infinity multiplied by infinity. Can the already full hotel accommodate this even more massive influx? Again, yes. And the techniques for doing so involve various clever schemes for assigning room numbers that can handle the various infinities involved. The mathematics gets more intricate, but the principle remains. As long as the infinities involved are of the same type, specifically the infinity of the natural numbers, the hotel can accommodate any number of additional infinite groups by appropriate rearrangement. What this thought experiment reveals is that infinity has properties that simply do not hold for any finite quantity. When you add 1 to a finite number, you get a different finite number. When you add 1 to infinity, you get the same infinity. When you double a finite number, you get a different finite number. When you double infinity, in the relevant sense, you get the same infinity. The basic arithmetic operations behave differently in infinite contexts than they do in finite ones. And the differences are not minor adjustments, but fundamental changes in how the operations work. I want to bring in here something that follows from these properties of infinity, but that may not be immediately obvious. The infinity that can accommodate any number of additional guests is the same infinity that we encounter when we count. The natural numbers are infinite in this specific way. There are infinitely many even numbers, infinitely many odd numbers, infinitely many prime numbers, infinitely many multiples of 3, infinitely many of any pattern you care to specify within the natural numbers. And yet all of these infinities are the same infinity in cardinal terms. The set of even numbers is the same size as the set of all natural numbers, even though the even numbers seem to be only half of the natural numbers. The intuition that a part should be smaller than the whole, which is true for finite quantities, fails for infinite ones. The part can be the same size as the whole. This is one of the defining properties of infinity, and it is what makes the mathematics of infinity so different from the mathematics of finite quantities. Now I want to take you a step further into the strangeness. Cantor, building on his work showing that the real numbers form a larger infinity than the natural numbers, demonstrated that there is an entire hierarchy of infinities extending upward without limit. He proved this through a technique called the diagonal argument, which I sketched in the previous part, and through related techniques that show how to construct larger infinities from smaller ones. Specifically, for any infinite set you can construct, the set of all subsets of that set is strictly larger. This is called the power set of the original set, and Cantor showed that the power set is always larger in cardinality than the original. So if you start with the infinity of the natural numbers, you can take its power set to get a larger infinity. You can take the power set of that to get a still larger infinity. You can continue this process indefinitely, generating a tower of infinities that extends upward without limit, with each level larger than all the levels below it. This raises a strange question. If the infinities themselves form an unending hierarchy, what is the cardinality of the collection of all infinities? The question turns out to be problematic in interesting ways. There cannot be a set of all infinities, because if there were, it would have a cardinality that would itself be either finite or infinite. If it were finite, it could not contain all the infinities, which extend upward without limit. If it were infinite, it would have to be one of the infinities in the hierarchy, but by construction, it would have to be larger than itself, which is contradictory. The hierarchy of infinities is therefore not itself a set in the standard mathematical sense. It is a proper class, a collection so large that the standard mathematical operations cannot be applied to it without producing contradictions. The very tools we use to think about infinity reach their limits when we try to think about the totality of infinities. And the resulting situation has been called, by some philosophers, the absolute infinite, which lies beyond mathematical analysis even after Cantor's work. This is genuinely vertiginous when you sit with it carefully. Mathematics has succeeded, against the expectations of most thinkers throughout history, in providing rigorous tools for analyzing infinity. But the analysis itself reveals limits, points beyond which the standard tools cannot reach, levels of infinity that exceed any framework we can develop for handling them. The hierarchy of infinities extends upward without limit, and the totality of this hierarchy lies beyond what can be coherently thought about within standard mathematical frameworks. We have gone deeper into infinity than anyone could have imagined 200 years ago, and we have found that infinity contains structures we still cannot fully comprehend. I want to bring in here a related puzzle that I find particularly thought-provoking. The continuum hypothesis, formulated by Cantor and listed by David Hilbert in 1900 as the first of his famous 23 problems for 20th century mathematics, asks whether there is any infinity strictly between the infinity of the natural numbers and the infinity of the real numbers. Cantor believed there was no such intermediate infinity, that the real numbers represent the next level of infinity above the natural numbers without any intermediate stage. This is the continuum hypothesis. The question turned out to be unexpectedly deep. In 1940, Kurt Gödel showed that the continuum hypothesis cannot be disproven from the standard axioms of set theory. In 1963, Paul Cohen showed that it cannot be proven from those axioms either. The continuum hypothesis is therefore independent of the standard mathematical foundations. It can be assumed to be true, in which case mathematics is consistent. It can be assumed to be false, in which case mathematics is also consistent. The standard tools cannot decide which assumption is correct. This is a genuinely strange situation. There is a clear, well-defined mathematical question. Either there is an intermediate infinity or there is not. The question seems to have a definite answer, in the sense that either the intermediate infinity exists or it does not. But the standard tools of mathematics cannot determine which is the case. The question is not just unsolved. It is, in some specific sense, undecidable within the framework of standard mathematics. Whether the question has a definite answer that we have not yet figured out how to prove, or whether the question is genuinely indeterminate at some deep level, is a matter of philosophical debate. Mathematicians continue to work on extensions of standard set theory that might decide the continuum hypothesis, but no extension has yet achieved general acceptance. The status of the continuum hypothesis remains one of the most genuinely puzzling features of contemporary mathematics, with implications that extend into the philosophy of mathematics and the question of whether mathematical reality is fully determined or whether it contains genuine indeterminacies. There is something almost humbling about this when you sit with it carefully. We have developed mathematical tools of extraordinary power. We have used them to investigate infinity, to demonstrate the existence of multiple sizes of infinity, to construct hierarchies of infinities that extend upward without limit. And the same tools, when applied to certain specific questions about infinity, encounter limits that prevent them from reaching definite answers. The mathematical universe, when explored thoroughly, contains regions that resist complete analysis, even with the most sophisticated tools we have developed. Whether these regions reflect genuine indeterminacies in mathematical reality, or whether they reflect limitations in our current tools that future developments might overcome, is a question that continues to be debated among philosophers of mathematics. Either way, the encounter with these limits is a reminder that the analysis of infinity, while it has come a long way since the ancient Greeks, has not exhausted the strangeness of the subject. There is more to infinity than we have yet figured out, and probably more than we will ever figure out, even with the continued development of mathematical tools across future centuries. So as you continue to drift, hold this image in your mind. Hilbert's Hotel, with its infinite rooms, accommodating its current residents, while still being able to welcome any number of additional guests through clever rearrangements. The hotel is full, but it is also somehow not full, in ways that no finite hotel could ever be. The mathematics of this strangeness is rigorous, but the underlying logic violates the intuitions we develop from finite experience. We are creatures of finite experience, encountering through mathematics a domain of infinite quantity that operates by its own rules, rules that do not match the rules we know from ordinary life. The encounter is genuinely strange, and the strangeness does not go away with familiarity. It becomes, perhaps, more interesting as we explore it more carefully, but it remains essentially strange. The infinities are not finite quantities scaled up. They are something different in kind, with their own logic, their own structure, their own surprising properties. Tonight, like every night you contemplate infinity, the strangeness is there, waiting to be encountered, ready to expand the mind that is willing to follow the careful arguments into the territory where ordinary intuitions break down and new kinds of understanding become available. Let me take you now into a different aspect of infinity, one that connects the abstract mathematics we have been examining to the concrete physical universe we inhabit. The question is whether the universe itself is infinite, and the answer turns out to be more interesting and more genuinely uncertain than the popular accounts of cosmology often suggest. Because the universe, when you actually examine the question carefully, may or may not be infinite, and the considerations on each side are worth thinking through patiently. Let me start with the basic situation. The observable universe, the portion of the universe from which light has had time to reach us since the Big Bang, is approximately 93 billion light-years across. This is a vast quantity, but it is finite. We can put a definite number on the size of the observable universe with reasonable precision, and the number is not infinite. Whatever is happening beyond the boundary of the observable universe is, by definition, beyond our capacity to directly investigate, since no signal from those regions has had time to reach us. The question of whether the universe extends beyond the observable region, and if so, how far, is therefore a question that cannot be settled by direct observation. We have to rely on theoretical considerations, on inferences from what we can observe, and on the mathematical models that describe the universe as a whole. What do these considerations suggest? The current state of cosmological evidence is consistent with several different possibilities for the overall structure of the universe. The universe could be spatially finite but unbounded, with the geometry curving back on itself in higher dimensions in such a way that a traveler heading in any direction would eventually return to their starting point, even though there would be no edge or boundary anywhere along the journey. This is analogous to how the surface of a sphere is finite but has no edge, with someone walking in any direction on the sphere eventually returning to where they started. The universe could be spatially infinite, extending forever in every direction, with the observable portion being just one small region of an unbounded whole. Or the universe could be finite, but with a boundary, though this option is less favored by current theoretical considerations because it raises problems about what happens at the boundary that have not been adequately addressed by any model. The available observational evidence cannot decisively distinguish between these possibilities. The geometry of the universe, as measured through various cosmological observations, appears to be very close to flat. A flat universe, in mathematical terms, is consistent with both the spatially finite case and the spatially infinite case. The flatness of the observable universe is therefore consistent with the universe as a whole being infinite, but it does not require the universe to be infinite. The data can be accommodated by either possibility, and the resolution depends on theoretical considerations that go beyond what current observations can directly establish. I want to draw out something that follows from these considerations, and that I think is genuinely strange when you sit with it carefully. If the universe is spatially infinite, then several remarkable consequences follow. The universe contains infinitely many stars, infinitely many galaxies, infinitely many planets. Whatever can happen anywhere in the universe is happening somewhere. Whatever combination of physical conditions is possible has been instantiated infinitely many times. If life can emerge in some range of conditions, then life has emerged in infinitely many places. If conscious creatures can develop, then conscious creatures have developed in infinitely many locations. If civilizations can arise, then civilizations have arisen, are arising now, and will arise in infinitely many regions of the cosmos. This is not just a quantitative observation about there being a lot of stuff. It is a qualitative observation about what an infinite universe must contain. In an infinite universe with the same physical laws operating throughout, every possibility that the laws permit must be actualized somewhere, and not just once, but infinitely many times. The implications for our sense of our own situation are striking. If the universe is infinite, then there are infinitely many regions exactly like the region we inhabit. There are infinitely many planets exactly like Earth. There are infinitely many copies of you reading these words in regions of the universe causally separated from ours, but containing the same arrangement of matter and the same patterns of thought. This is sometimes called the Level 1 multiverse, distinguished from the various other multiverse concepts that have been proposed by physicists. It does not require any additional theoretical machinery beyond the assumption that the universe is spatially infinite and that the physical laws operate the same way throughout. Given infinite space and the same physics, every finite arrangement of matter that is compatible with the laws must occur infinitely many times, simply because there are infinitely many opportunities for the arrangement to occur, and only a finite number of distinct arrangements within any bounded region. The mathematics is straightforward, but the implications are vertiginous. Some physicists have pushed back against this conclusion, pointing out that we do not actually know whether the universe is spatially infinite, and that the assumption of infinite space introduces complications that may indicate the assumption is wrong. The actual physical universe may be finite, with the apparent flatness of the observable region reflecting some larger curved structure that we cannot directly perceive. Or the physical laws may vary across regions of the universe in ways that prevent the simple replication argument from going through. Or there may be other considerations we have not yet identified that prevent the infinite universe from having the consequences that the simple argument suggests. The honest position is that we do not know whether the universe is infinite, and we therefore do not know whether the strange consequences of cosmic infinity actually obtain in our universe. But I want to pursue the implications a little further, because they are interesting, regardless of whether they actually apply to our universe. If the universe is infinite, then the relationship between the local and the global becomes very strange. Your individual life, with all its specific details, is being replicated infinitely many times across the cosmos. Every choice you make, every thought you have, every moment of your existence is being made and had and experienced infinitely many times by infinitely many copies of you in regions causally separated from each other. This raises questions about personal identity that are genuinely difficult. Are these copies of you actually you in some meaningful sense? Or are they merely structurally identical individuals who are not connected to your specific subjective experience? The question is hard, and there is no consensus among philosophers about the right way to answer it. There is a related consequence that I find equally strange. In an infinite universe with the appropriate physical laws, every possible variation on your life is also being lived somewhere. There are versions of you who made different choices at every decision point. There are versions of you who never were born because of different reproductive outcomes among your ancestors. There are versions of you who lived to ages you have not yet reached and who experienced events you have not yet experienced. The full range of possible lives compatible with the basic patterns of human existence is being instantiated infinitely many times in regions of the universe that we cannot reach or observe, but that, on the assumption of cosmic infinity, must exist. The traditional response to these speculations is to point out that they are precisely speculative, that we do not know whether the universe is actually infinite, and that the implications of infinite cosmology should be treated as interesting possibilities rather than as established facts. This is a reasonable response, and I want to take it seriously. But the speculations are not fanciful. They follow from a relatively simple set of assumptions that are at least consistent with the available evidence. Whether the assumptions are actually correct is unknown, but the implications of their being correct are worth thinking about, both for what they would mean if true, and for what they tell us about the strange consequences of cosmic infinity in general. Let me now turn to a different aspect of physical infinity that has been particularly troublesome for contemporary physics. Various physical theories produce predictions of infinite quantities that do not seem to correspond to anything physically real. The most famous example is the so-called ultraviolet catastrophe in classical physics, which predicted that the radiation emitted by hot objects should contain infinite energy at high frequencies. This prediction was clearly wrong, since hot objects do not emit infinite energy. The resolution of the ultraviolet catastrophe was one of the early triumphs of quantum mechanics, with the development of new physical principles that prevented the infinite energy from being predicted. But other infinities continue to appear in physical theories, particularly in quantum field theory, where the calculations of various physical quantities yield infinite values that have to be removed through technical procedures called renormalization before the theories can be compared with experiment. The renormalization procedures work in the sense that they produce finite predictions that agree with experimental measurements to extraordinary precision. But the philosophical status of these procedures has been debated for decades. Are the infinities that emerge from quantum field theory indications that the theories are incomplete in some important way, with the infinities being symptoms of a deeper problem that has not yet been fully understood? Or are the infinities mathematical artifacts of how we have formulated the theories, with the renormalization procedures correctly removing them to produce the genuine physical predictions? Different physicists have different opinions on this, and the question has not been definitively resolved. The infinities that appear in quantum field theory may be telling us something profound about the limitations of our current physical theories, or they may be telling us about the limitations of how we have chosen to formulate those theories. Either way, the role of infinity in fundamental physics is an active area of investigation, with implications for our understanding of how reality is structured at the deepest levels. There is one more aspect of physical infinity I want to mention before we close this part. Black holes, those collapsed massive objects that are now well-established features of the universe, contain at their centers what physicists call singularities. A singularity is a point at which various physical quantities, including density and curvature of space-time, become infinite. The singularities at the centers of black holes are predictions of general relativity, and they are widely interpreted as indications that general relativity breaks down under the extreme conditions inside black holes. The actual physics at the centers of black holes is presumably described by some more complete theory that combines general relativity with quantum mechanics, a theory that we do not yet have. The infinities that general relativity predicts at black hole centers are therefore probably not real physical infinities, but indications that our current theories cannot describe what is actually happening at those locations. The singularities at the beginning of the Big Bang, similarly, are widely interpreted as indications that our current theories cannot describe the very earliest moments of cosmic history. Where general relativity predicts infinite density, the actual physics is probably finite, but described by laws we have not yet worked out. So as you continue to drift, hold this image in your mind. The universe extending around you in every direction, with the observable portion being only the small region from which light has had time to reach us. Beyond that observable boundary, the universe may continue forever, infinite in extent, containing an infinite number of stars and galaxies and planets, and possibly conscious beings. Or it may eventually end, in some configuration we cannot directly perceive. The question of which possibility actually obtains is one we cannot currently answer. But the contemplation of cosmic infinity, regardless of whether it is the actual situation we live in, is one of the genuinely vertiginous experiences available to thinking creatures who have learned to think carefully about the implications of large-scale physical theories. We exist in a universe whose ultimate extent we do not know, surrounded by quantities of space and matter that may genuinely have no end. The smallness of our own situation against this potentially infinite background is part of what makes contemplation of cosmic scale so strange and so worthwhile. There is a category of paradox that infinity produces, beyond the ones we have already encountered, that I want to walk you through tonight, because it touches questions about the nature of reality and our capacity to think coherently about extreme situations. The paradoxes of infinity are not just historical curiosities. They continue to pose genuine difficulties for anyone trying to think carefully about infinite quantities, and the various proposed resolutions of these paradoxes reveal interesting features of how we understand reality. Let me start with what may be the strangest infinity paradox, sometimes called the Ross-Littlewood paradox, after the mathematicians who developed it. Imagine an empty container and an infinite supply of numbered balls. Starting at 1 minute before noon, you perform the following operation. You place balls numbered 1 through 10 into the container, then you remove ball number 1. At 30 seconds before noon, you place balls numbered 11 through 20 into the container, then you remove ball number 2. At 15 seconds before noon, you place balls numbered 21 through 30 into the container, then you remove ball number 3. You continue this pattern, with each operation occurring at half the time interval before noon as the previous operation. The intervals form a converging series that adds up to 1 minute, so all the operations are completed exactly at noon. The question is, how many balls are in the container at noon? The puzzle has multiple answers depending on how you analyze it, and the multiplicity of answers is itself the point. From one perspective, it seems obvious that the container should contain infinitely many balls at noon, because at each step you are adding 10 balls and removing only 1, for a net gain of 9 balls per step, and there are infinitely many steps. After infinitely many net gains of 9 balls each, the container should contain infinitely many balls. From a different perspective, it seems equally obvious that the container should be empty at noon, because every ball that was ever placed into the container has a specific number, and every numbered ball is removed at some specific step. Ball number 1 is removed at the first step. Ball number 2 is removed at the second step. Ball number n is removed at step n. Every ball has been removed by the time noon arrives. Therefore, the container is empty. These two analyses cannot both be correct. The container cannot simultaneously contain infinitely many balls and no balls. But each analysis seems valid given its own assumptions, and the difference in conclusions reflects different ways of thinking about what happens when an infinite series of operations is completed. The paradox is genuinely difficult, and it does not have a generally accepted resolution. Some mathematicians argue that one analysis is correct and the other is mistaken, but they disagree about which is which. Others argue that the paradox reveals something problematic about the very assumption that an infinite series of operations could be completed at all, suggesting that the scenario is not coherently describable. Still others argue that the paradox shows that our ordinary concepts of containers and contents do not extend cleanly to infinite contexts, with the question of what is in the container at noon being genuinely indeterminate rather than having any specific answer. What I find genuinely interesting about this paradox is what it reveals about the limits of intuitive reasoning when applied to infinite contexts. We have intuitions about containers and balls that work perfectly well for finite scenarios. We can extend these intuitions to infinite scenarios in two different ways, both of which seem reasonable. and the extensions yield contradictory conclusions. This suggests that our intuitions do not actually settle questions about infinite scenarios, even when we feel like they should. The intuitions reach their limits at the boundary between finite and infinite, and beyond that boundary, careful mathematical analysis is required to determine what can and cannot be coherently said. Let me bring in another paradox that has occupied philosophers for a long time, sometimes called the Galileo paradox, after the Italian astronomer who first articulated it clearly. Galileo noticed that there are infinitely many natural numbers and infinitely many perfect squares, with the perfect squares being a subset of the natural numbers. Every perfect square is a natural number, but not every natural number is a perfect square. So you might expect there to be more natural numbers than perfect squares. But Galileo also noticed that you can put the natural numbers and the perfect squares into one-to-one correspondence. The natural number 1 corresponds to the perfect square 1. The natural number 2 corresponds to the perfect square 4. The natural number 3 corresponds to the perfect square 9. In general, the natural number n corresponds to the perfect square n squared. Every natural number has exactly one perfect square corresponding to it, and every perfect square has exactly one natural number corresponding to it. By this measure, there are exactly as many perfect squares as there are natural numbers. This is paradoxical because the perfect squares are clearly a proper subset of the natural numbers. There are natural numbers that are not perfect squares, like 2 and 3 and 5 and so on. So the perfect squares should be smaller than the natural numbers, in the sense that you can find natural numbers that are not in the smaller collection. Yet by the one-to-one correspondence, the two collections are the same size. The whole and a proper part of the whole turn out to be the same size, in the relevant infinite sense. Galileo was so disturbed by this that he concluded that the relations of larger, smaller, and equal simply do not apply to infinite quantities. The categories that work for finite quantities, in his view, broke down at infinity, and we should not try to extend them. Galileo was almost right, but not quite. Cantor, working 2 centuries later, showed that the relations of larger, smaller, and equal can be extended to infinite quantities, but they have to be defined more carefully than the intuitive notions suggest. The proper extension involves the concept of one-to-one correspondence. 2 infinite collections have the same size if and only if they can be put into one-to-one correspondence with each other. By this definition, the natural numbers and the perfect squares are the same size, even though the perfect squares are a proper subset of the natural numbers. The intuition that a proper subset must be smaller than its containing set is correct for finite collections, but fails for infinite ones. And the precise mathematical definition of size for infinite collections allows the part to be the same size as the whole. This is one of the defining properties of infinite collections, and it can be used as a definition of what infinity means in mathematical contexts. A collection is infinite if and only if it can be put into one-to-one correspondence with one of its proper subsets. Finite collections cannot have this property. If you have a finite collection of, say, 10 things, and you remove one of them, you have a collection of 9 things, which cannot be put into one-to-one correspondence with the original collection of 10. But if you have an infinite collection like the natural numbers, you can remove one or any finite number of elements, or even infinitely many elements, as long as you do it in the right way, and still have a collection that can be put into one-to-one correspondence with the original. The part can equal the whole in infinite contexts, in ways that simply do not happen for finite quantities. Now I want to address something even stranger that follows from these properties. Consider the rational numbers, which are all the numbers that can be expressed as fractions of integers. The rational numbers seem like they should be a much larger collection than the natural numbers, because between any two natural numbers, there are infinitely many rational numbers. Between 0 and 1, for instance, there are rational numbers like 1/2, 1/3, 1/4, and infinitely many other fractions. Between 1 and 2, there are similarly infinitely many rationals. And between any two rationals, there are again infinitely many other rationals, with no minimum spacing between them. The rationals appear, intuitively, to be densely packed throughout the number line in ways that the natural numbers are not. Yet despite this apparent density, the rational numbers turn out to be the same size as the natural numbers in cardinal terms. They can be put into one-to-one correspondence with the natural numbers through a clever counting scheme. The standard demonstration involves arranging the rational numbers in a two-dimensional grid, with rows corresponding to numerators and columns corresponding to denominators, and then reading off the rationals in a diagonal pattern that visits every grid position exactly once. This counting scheme, called the diagonal method, or sometimes the snake counting, demonstrates that the rationals can be enumerated in a sequence, with each rational appearing at a specific position in the sequence. Because the rationals can be enumerated in this way, they have the same cardinality as the natural numbers. They are countable in the technical sense. The apparent density of the rationals does not make them larger than the natural numbers in cardinal terms. This is genuinely surprising. The rationals seem like they should be vastly more numerous than the natural numbers, given how densely they pack the number line. But the careful mathematical analysis shows that they are the same cardinal size. The two collections, despite their very different geometric distributions, have the same number of elements when number is properly defined for infinite contexts. The intuition about density does not match the mathematical reality about cardinality, and the divergence between intuition and reality is one of the recurring features of working with infinite quantities. The real numbers, in contrast, turn out to be genuinely larger than the natural numbers in cardinal terms. We saw this in the first part of our exploration through the diagonal argument. The real numbers cannot be put into one-to-one correspondence with the natural numbers, no matter how clever the counting scheme. They form a strictly larger infinity. So we now have a clear picture. The natural numbers, the integers, the rational numbers, and various other countable collections are all the same cardinal size, the smallest infinite size. The real numbers, the complex numbers, and various other uncountable collections form larger infinities. The hierarchy of infinities is real, and it has specific structure. Let me push this further. Within the real numbers, are there sets that are countable, even though the real numbers as a whole are uncountable? Yes, there are. The algebraic numbers, which are the real numbers that are roots of polynomial equations with integer coefficients, are countable, even though they include many of the real numbers we work with most often, including the rationals and the various roots, like the square root of 2. The transcendental numbers, which are the real numbers that are not roots of any polynomial equation with integer coefficients, are uncountable. The transcendentals include numbers like pi and e, and they form the bulk of the real numbers in cardinal terms. Almost all real numbers, in a precise mathematical sense, are transcendental, even though the algebraic numbers seem to occupy a substantial portion of the number line. The intuition that the real numbers are mostly the familiar ones we know how to construct turns out to be wrong. The familiar real numbers are vastly outnumbered by the unfamiliar transcendentals, with most real numbers being numbers we can describe only in general terms, rather than through specific constructions. I want to bring in here something that I find genuinely vertiginous about this situation. Almost every real number is a number we cannot describe explicitly. The numbers we can name, the numbers we can construct through any specific procedure, the numbers we can pick out through any finite description, are an exceptionally small subset of the real numbers as a whole. Most real numbers are, in some sense, beyond our descriptive capacity. They exist mathematically, in the sense that they are part of the real number system. But they cannot be picked out individually by any finite process. The vast majority of mathematical reality, in this sense, is beyond direct human access, with us being able to interact only with the relatively small subset that admits of explicit description. This is a strange feature of mathematics that has implications worth considering. The mathematical universe contains entities that are real in the technical mathematical sense, but that no human will ever specifically encounter or work with. The numbers that have not been named, the functions that have not been described, the structures that have not been constructed, are vastly more numerous than the ones that have been. We are, in our mathematical activity, navigating a small island of named and described entities in an ocean of mathematical reality that is mostly beyond our direct engagement. Whether this larger ocean of mathematical reality really exists, in some metaphysical sense, or whether it is merely a manner of speaking that emerges from our formal systems, is one of the deeper questions in the philosophy of mathematics. But the formal mathematics is clear about its existence in the technical sense, with the implications for our understanding of mathematical reality being genuinely strange when you sit with them carefully. So as you continue to drift, hold this image in your mind. The number line stretching out in both directions, with the integers marked at regular intervals, the rationals densely packed between them, and the irrationals filling in the spaces between the rationals to produce the continuous flow of the real numbers. Most of the points on this line are transcendental numbers that no one has ever named or constructed. They exist mathematically, in their specific positions on the line, but no human has ever picked them out or worked with them individually. They are as real as pi or e in the technical mathematical sense, but they have no names, no descriptions, no specific roles in any human mathematical practice. The number line is mostly populated by these unnamed numbers, with the named numbers being a tiny minority of the total. We work with a small known portion of the real numbers, while the vast majority remains unnamed and unknown. The mathematical universe extends far beyond what we have explicitly investigated, in directions we have not yet fully mapped, with most of its inhabitants being entities we will never specifically meet. The contemplation of this, on a quiet night like this one, is one of the strange pleasures available when we let ourselves think carefully about the structure of mathematical reality. There is a particular relationship between infinity and time that I want to explore tonight, because the temporal dimension of infinite quantities raises questions that go beyond what we have discussed in connection with infinite spaces and infinite collections. The questions about temporal infinity touch some of the deepest issues in cosmology and philosophy, and they have been debated since the earliest periods of human thought about the nature of existence. Let me start with the basic question: has time always existed, or did time itself have a beginning? The intuitive response for most people is that time must have always existed, because the alternative seems incoherent. If time had a beginning, what was happening before that beginning? The very idea of before suggests time, so any beginning of time would have to be preceded by something temporal, which contradicts the idea that time itself was beginning. By this reasoning, time must extend backward forever, with no first moment. But this intuitive argument runs into difficulties when you examine it carefully. Saint Augustine, working in the 4th and 5th centuries, addressed exactly this question and came to a different conclusion. He argued that time itself was created along with the rest of the world, and that asking what happened before time began is like asking what is north of the North Pole. The question presupposes a framework that does not apply. There is no before time in this view, because the concept of before requires time to exist. Time is not a container within which events occur. Time is itself part of the structure of the world, and like everything else in the world, it had a beginning. The question of what came before is therefore not just unanswered, but malformed. It does not refer to anything coherent. This Augustinian view remained influential throughout Western religious and philosophical thought, but it was contested by various other traditions that argued for the eternity of the world. The Aristotelian tradition, which dominated medieval philosophy in various modified forms, generally held that the world was eternal in the past, with time extending backward without limit. The argument for this position drew on various considerations about causation, with the basic claim being that every event must have a cause, and the chain of causes must extend backward forever, since there could not be a first cause without something before it to bring it into being. Different philosophers worked out different versions of this argument, but the underlying claim was that the universe must be eternal, with time extending backward through an infinite past. The dispute between these two views, the temporal beginning view associated with Augustine and the eternal universe view associated with Aristotle, occupied much of medieval philosophy. The dispute had religious dimensions, with various theological traditions taking different positions, and it had genuinely difficult philosophical aspects that continue to be debated today. The question is not just whether the universe began in time, but whether the very concept of time can be coherent without some sort of beginning, or whether the concept of beginning can be coherent without time already existing to make sense of beginnings. Modern cosmology has added its own complications to these old debates. The Big Bang theory, which we discussed in an earlier exploration, suggests that the observable universe began approximately 14 billion years ago in a hot, dense state, with time and space themselves emerging from this initial event. According to this view, the question of what happened before the Big Bang may be malformed in a way similar to what Augustine suggested. There may be no before, because time itself began with the Big Bang. The cosmology has thus given empirical support, of a sort, to the Augustinian view, with the technical details being different, but the basic structure being similar. But cosmology has also produced alternative views in which time extends backward beyond the Big Bang. Various theories propose that the Big Bang was not the beginning of time, but rather a transition between earlier and later phases of cosmic history. Cyclic cosmologies suggest that the universe undergoes endless cycles of expansion and contraction, with each Big Bang being followed eventually by a contraction to a big crunch, which then bounces back into another Big Bang. In these views, time extends backward through infinitely many previous cycles, with no first cycle and no absolute beginning. Alternative theories propose that our Big Bang was the result of processes occurring in a larger structure that existed before our universe, with various forms of multiverse theory suggesting that universes are continually being created in some larger framework that may itself extend backward without limit. The honest position on these competing views is that we do not currently know which is correct. The empirical evidence we have access to does not extend back beyond the Big Bang itself, and any theory that proposes a pre-Big Bang state has to work without direct observational support for that proposal. Different theories make different predictions about what we should observe in the available evidence, But none of these predictions has been decisive enough to rule in or rule out any of the major competing views. The question of whether time had a beginning, in the sense of being finite in the past, or whether time extends backward forever, is therefore one of the genuinely open questions in contemporary physics and philosophy. I want to draw out what is at stake in this question because it has implications for how we think about the universe and our place in it. If time had a beginning, then the universe is finite in temporal extent in the past direction. Whatever came into existence at the moment of the beginning constitutes the totality of cosmic history, with a definite first moment and a definite duration extending from that moment to the present. If time has no beginning, then the universe is temporally infinite in the past direction. There has been an infinite duration before any specific moment, with infinitely many previous events leading up to the current state of affairs. The two views imply quite different cosmic situations, with different implications for various theological, philosophical, and even ethical questions. Now I want to turn to the question of the future, which has its own interesting features. Will time continue forever, or will it have an end? The question is somewhat more tractable than the question about the past, because we have some basis for projecting the future of the universe based on what we know about its current state and the physical laws that govern its evolution. The current cosmological consensus suggests that the universe will continue to expand forever, with the expansion accelerating due to dark energy. This continued expansion has various implications for the long-term future of the cosmos. In the relatively near future, by cosmic standards, the universe will continue to look much as it does now. Galaxies will continue to form stars. Stars will continue to burn through their fuel and die, and the basic patterns of cosmic activity will continue. But over much longer timescales, things will change dramatically. As the universe expands, the matter within it will become more diluted, and the rate of star formation will gradually decrease. Eventually, in something like 100 trillion years, the last stars will burn out, and the universe will enter a phase in which no new stars are being formed, and the existing stars have all died. This is sometimes called the degenerate era of cosmic history. Beyond the degenerate era, the universe enters even stranger phases. The cold remnants of dead stars will gradually decay through various processes, including the slow evaporation of black holes through Hawking radiation. Eventually, in timescales of perhaps 10 to the 100th power years, all matter will have evaporated, and the universe will consist of nothing but a thin gas of photons and other elementary particles spread across an unimaginably vast and cold space. This is sometimes called the heat death of the universe, the state of maximum entropy in which no useful work can be done and no further interesting events can occur. But here is where the question of temporal infinity becomes interesting. The heat death is a state, not an ending. Once the universe reaches heat death, it does not stop existing. It just continues, in its dispersed and inert state, forever. Time does not end at heat death. Time continues, but nothing interesting is happening anymore. The universe sits in its final state, with the same basic configuration extending forward through infinite future time, with no further significant changes. This is, when you sit with it carefully, a strange picture. The universe has a finite period of interesting activity, perhaps lasting some quadrillions of years from beginning to heat death, and then an infinite period of inert continuation. The interesting part of cosmic history is finite, but the boring continuation that follows is infinite. Almost all of cosmic time in this picture is the inert post-heat death era. The era we currently occupy, with stars and galaxies and life, is a vanishingly small fraction of the total cosmic duration. Some physicists have raised interesting questions about what happens during the infinite post-heat death era. If quantum effects continue to operate, then random fluctuations may occasionally occur in the otherwise uniform thin gas of particles. Most of these fluctuations will be small and will dissipate without producing anything interesting. But over the infinite future timescale, even extremely improbable fluctuations will occasionally occur. Given infinite time, even fluctuations that would produce, say, a fully formed brain with specific memories and experiences must occasionally arise from random rearrangements of the particles in the post-heat death universe. This is sometimes called the Boltzmann brain problem, after the physicist Ludwig Boltzmann, who first considered such issues. The Boltzmann brain problem has interesting implications. If the universe will continue forever after heat death, and if random fluctuations during this infinite era occasionally produce conscious observers, then the total number of Boltzmann brains that will exist in cosmic history vastly exceeds the number of ordinary brains that exist during the early period when stars and planets and biological evolution can support normal life. By this reasoning, almost all conscious observers in the universe should be Boltzmann brains, rather than ordinary brains. The fact that we are apparently ordinary brains, with consistent memories and a coherent picture of the world, becomes statistically unlikely if Boltzmann brains vastly outnumber us. This reasoning has been used to argue that something must be wrong with the standard cosmological picture, since we should not expect to be in such a statistically unlikely situation. The Boltzmann brain problem has not been definitively resolved. Different physicists have proposed different ways to handle it, including various modifications to the standard cosmology that prevent Boltzmann brains from dominating the cosmic population of observers. The problem itself is taken seriously enough that it has generated substantial technical literature, with the implications of infinite future time for the nature of conscious observers being one of the genuinely strange consequences of taking cosmic infinity seriously. I want to bring in here something that I find genuinely interesting about the relationship between temporal infinity and personal identity. If the universe continues forever, and if the same physical laws operate throughout, then the configuration of matter that constitutes you, with all your specific memories and traits, must eventually recur somewhere in the future, simply by random fluctuations producing the same arrangement of particles that constitutes you now. The probability of this recurrence is extraordinarily low for any specific moment, but with infinite time available, even extraordinarily low probabilities eventually result in occurrence. So, in some far future moment, the universe will contain another version of you, identical in every physical respect, with the same memories and the same patterns of thought. Whether this future version of you would be you in some meaningful sense, or whether it would be a different person who happens to be physically identical to you, is a question that admits of different answers depending on one's views about personal identity. The classical view that personal identity requires continuous physical or psychological connection would deny that the future version is you, since there is a vast gap of time between you and that version with no continuous existence connecting them. A different view that grounds personal identity in physical or psychological structure rather than continuity would say the future version is you, since it has all your specific characteristics. The choice between these views has implications for how we think about ourselves across cosmic time. And the issue is not merely abstract, because the implications affect how we should think about our own potential continuation in various scenarios involving long timescales. There is one more aspect of temporal infinity I want to address before we close this part. The various religious and philosophical traditions have developed many different frameworks for thinking about temporal infinity, often connected to ideas about eternity and divinity. The notion of God as eternal in many traditions has been understood not as God existing through infinite time, but as God existing outside of time entirely. The eternal, in this sense, is not the same as the infinitely long-lasting. The eternal is timeless, while the infinitely long-lasting is something that exists within time and continues without end. The distinction is subtle but significant, and it allows for different ways of thinking about the relationship between time and reality. The eternal, in the timeless sense, is not constrained by temporal sequence, and its relationship with the temporal world is therefore different from the relationship that any temporal entity could have with the world. Various philosophical traditions have developed elaborate frameworks for thinking about eternal versus temporal existence, with the implications being significant for how we understand the nature of fundamental reality. So as you continue to drift, hold this image in your mind. Time stretching out before you and behind you, in dimensions whose total extent we do not know. The past may be infinite, with infinitely many previous events leading up to this moment. The future may be infinite, with infinitely many subsequent events following from this moment. Or one or both of these dimensions may be finite, with definite boundaries somewhere in the deep past or the distant future. We do not know which is the actual situation, despite all the work of cosmologists and philosophers across many centuries. What we know is that we exist in this specific moment, briefly conscious of our own existence, surrounded by a temporal extent that may or may not have boundaries in either direction. Our individual lives are vanishingly small compared to even the relatively short cosmic timescales that we can confidently discuss, much less the potentially infinite ones that may lie beyond our ability to investigate. The contemplation of temporal infinity on a quiet night like this one is itself a kind of acknowledgement of how much larger the temporal universe is than the brief moments of our own existence within it. We are very small, in temporal terms, but the smallness does not make our moments meaningless. It places them within a context that is larger than we can fully comprehend, which is itself one of the strange privileges of being conscious creatures who can think about our place in time at all. There is a particular intersection between infinity and the concept of probability that I want to walk you through tonight, because the application of probability to infinite contexts produces results that are genuinely strange and that have implications for how we think about chance, possibility, and what counts as remarkable. The mathematics of infinite probability is one of those domains where intuitions developed for finite contexts simply fail, and the failures reveal something interesting about the nature of probability itself. Let me start with a famous thought experiment. Imagine an infinite collection of monkeys, each typing randomly on a typewriter for an infinite amount of time. The classical version of this thought experiment asks whether the monkeys would eventually produce the complete works of Shakespeare. The intuitive answer is yes, because given infinite time and infinitely many monkeys, every possible sequence of letters must eventually be produced, including the specific sequence that constitutes Shakespeare's complete works. The probability of any specific finite sequence being produced approaches certainty as the number of attempts approaches infinity, so the production of Shakespeare's works becomes essentially guaranteed. This thought experiment is often used to illustrate the strange behavior of probability in infinite contexts, and it captures something important. Events that have arbitrarily small but non-zero probability of occurring in any finite trial become essentially certain to occur given infinite trials. The very nature of probability changes when applied to infinite contexts. Things that we would consider impossibly unlikely become certain. Things that seem like they could not possibly happen by chance become guaranteed to happen, given enough chances. But the implications go further than the simple version of the thought experiment suggests. If you have infinite monkeys typing for infinite time, they do not just produce Shakespeare's complete works once, they produce them infinitely many times. They produce every possible variation on Shakespeare's works. They produce every book that has ever been written, and every book that could ever be written. They produce every possible sequence of characters of every possible length. The output of the infinite monkey scenario, in the limit, contains every possible textual production, with each specific text being produced infinitely many times. This is a strange consequence, and it reveals something important about what infinite probability actually means. In an infinite context with the appropriate randomness, every possible event that has any non-zero probability occurs not just once, but infinitely many times. The very rare and the very common happen with the same essential certainty. The mundane and the extraordinary both happen infinitely often. The distinction between common and rare events, which structures our finite experience, becomes meaningless in the relevant sense, because all events with any positive probability happen infinitely many times. I want to bring in here a concept that may be unfamiliar, but that is genuinely interesting. The mathematics of infinite probability requires distinguishing between events that have probability zero and events that are impossible. In finite contexts, these are essentially the same thing. If something has probability zero of happening, it does not happen. If something cannot happen, it has probability zero. The two categories coincide, but in infinite contexts, they come apart. There are events with probability zero that nevertheless do happen, and there are events that cannot happen at all, and these are different categories. Consider the following. You have an infinitely long random sequence of digits, with each digit being chosen independently and uniformly from 0 through 9. What is the probability that the sequence is exactly the decimal expansion of pi? The answer is 0. Each specific infinite sequence has probability 0, because there are infinitely many possible sequences, and the probability is distributed among all of them. Yet some specific infinite sequence does occur, and whatever sequence occurs had probability 0 before it occurred. So events with probability 0 can and do happen. The probability 0 just means that the event is one of infinitely many equally specific events, not that the event is impossible. This may seem like a technical point, but it has implications that I think are genuinely strange. In any infinite probabilistic setting, individual specific outcomes have probability 0, even though some specific outcome must occur. The very specificity of the outcome that does occur was, before it occurred, a probability 0 event. This means that whenever something specific happens in an infinite probabilistic context, what has happened was, in some technical sense, infinitely unlikely. Yet it happened because something had to happen, and whatever happens has the same essential property of having been infinitely unlikely beforehand. Some philosophers have applied this kind of reasoning to questions about cosmic existence. If the universe involves infinite probabilistic processes, then everything specific that occurs is, in this technical sense, infinitely unlikely. Our specific existence, with its specific details, is one specific outcome among infinitely many possible outcomes that the underlying processes could have produced. The fact that our specific existence has occurred is therefore, in the technical sense, infinitely unlikely. But something had to occur, and our existence is one of the things that has occurred. The question of whether this implies anything significant about cosmic design or chance has been debated for a long time, with different philosophers drawing different conclusions from the same basic mathematical structure. I want to push this further into territory that connects with our earlier discussions about the multiverse. We considered earlier that an infinite spatial universe with the same physical laws operating throughout would contain every possible arrangement of matter, with each arrangement being instantiated infinitely many times. The mathematics is similar to the infinite monkey scenario. Given infinite trials, every possible outcome with non-zero probability occurs infinitely many times. If the universe is spatially infinite and the basic physics is consistent, then every possible configuration of a finite region of matter occurs somewhere, and every such configuration occurs infinitely many times. This means that the universe, on the assumption of spatial infinity, contains infinitely many copies of you, infinitely many variations of you who made different choices, infinitely many variations of human history with different specific events, infinitely many planets like Earth with different specific developments, infinitely many of every possible thing that could exist within the basic constraints of physics. The conditional is important. We do not know whether the universe is actually spatially infinite. But if it is, the implications are these. The strangeness of these implications has led some thinkers to reconsider the assumption of cosmic infinity. The argument goes something like this. We do not have direct evidence that the universe is infinite. The standard cosmological models are consistent with infinite space, but they do not require it. The strange implications of infinite space, including the existence of infinitely many copies of every observer, may be a reason to question whether the universe is actually infinite. Perhaps the universe is finite but very large, with the strange implications of infinity not actually applying. The argument is not decisive, since the implications of infinity might just be features of reality that we have to accept, but it represents one philosophical response to the strange consequences of cosmic infinity. There is another aspect of infinite probability that I want to address, because it touches questions about what we should expect to observe. The argument is sometimes called the doomsday argument, and it has generated substantial debate among philosophers and statisticians. The basic idea is this. If you assume that you are a randomly selected observer from among all the humans who will ever exist, and if you reason about the probability of your existence at various points in human history, you can derive probabilistic conclusions about the total number of humans who will ever exist. The reasoning goes as follows. If humanity will eventually produce 100 billion total humans, and if you are randomly selected from this population, then the probability of your being among the first 10% of humans is 10%. The probability of your being among the first 1% is 1%. The probability of your being in any specific range of the population can be calculated based on the assumption of random selection. Now consider what we know about your situation. You are roughly the 70 or 80 billionth human to have existed, depending on how the counting is done. If humanity will produce vastly more humans in the future, with the eventual total being trillions or more, then your position as one of the first 80 billion would be statistically very unlikely. If humanity will produce only a relatively small number more, with the eventual total being something like 100 or 200 billion, then your position would be more typical. The doomsday argument concludes that the more typical position is more likely to be correct, and therefore that humanity will not produce vastly more humans in the future. The argument has been used to derive specific probabilistic estimates of how long humanity will continue to exist. The doomsday argument is controversial, and various counterarguments have been proposed. Some critics point out that the argument depends on contestable assumptions about what counts as a random selection from the human population. Others argue that the argument confuses different ways of thinking about probability. Still others accept the basic structure of the argument, but argue that the specific numerical conclusions are sensitive to details of the assumptions in ways that make the conclusions less compelling than they might initially appear. The argument has not been decisively refuted, but it has not been generally accepted either, and it remains one of the more contested topics in the philosophy of probability. What I find interesting about the doomsday argument is what it reveals about how we should think about our own existence. Each of us exists at some specific position in the history of conscious beings on this planet. The position we occupy is in some sense random with respect to the larger sweep of cosmic history. We could have existed at any moment in the history of conscious beings, and we happen to exist now. The implications of this random positioning, when carried through carefully, lead to conclusions that are at least surprising and possibly disturbing. We are statistical samples from the population of conscious beings that exists across cosmic time, and the patterns we observe in our own situation may be informative about the larger population from which we have been drawn. Whether this reasoning is correct is genuinely debated, but the underlying perspective is worth considering, regardless of whether it leads to specific conclusions. The recognition that we are participants in a much larger pattern of conscious existence, that our specific moment is one of many possible moments at which conscious beings could exist, and that the patterns of our own situation may reflect features of this larger pattern, is one of the more vertiginous applications of probabilistic thinking to questions about our own existence. The contemplation of these questions does not yield definitive answers, but it does open up perspectives that ordinary thinking does not naturally provide. There is one more aspect of infinite probability I want to address before we close this part. The relationship between infinity and randomness is deeper than the simple infinite monkey scenario suggests. In probability theory, there are subtle issues about how to define random selection from infinite collections, and these issues have implications that bear on various paradoxes that arise when you try to apply probabilistic reasoning to infinite contexts. The mathematics gets technical, but the basic point is that not every infinite collection admits of a well-defined uniform random distribution. Some infinite collections have natural ways to define randomness on them, while others resist such definitions in ways that produce paradoxical results. This is significant because it shows that infinity does not automatically produce well-behaved probabilistic structures. The mathematical analysis of infinite probability requires careful attention to which definitions of randomness are coherent and which are not. Various paradoxes that arise in infinite probabilistic settings, including some that have generated substantial philosophical discussion, turn out to depend on assumptions about randomness that cannot be coherently maintained in infinite contexts. The careful analysis of these paradoxes reveals limitations in our intuitions about randomness when applied beyond the finite cases where the intuitions were originally developed. So, as you continue to drift, hold this image in your mind. An infinite collection of typing monkeys, generating sequences of letters at random, producing in their cumulative output every possible text that could ever be written. Among the infinite output are the complete works of Shakespeare, of course, but also every other book that has been written and every book that could be written, each appearing infinitely many times in slightly different versions and contexts. The infinite output contains every possible scientific paper, every possible philosophical argument, every possible poem, every possible essay, every possible piece of writing of every possible length. It contains the full history of every possible variation on human civilization, each rendered in the random output of the typing monkeys. The output also contains, by the same reasoning, descriptions of universes very different from ours, with different physical laws, different biological possibilities, different cultural developments. The infinite monkeys, given infinite time, generate the entire space of possible texts that could ever be produced. We can think about this space, even though we cannot directly access most of it. The contemplation of this infinite space of possible texts is itself a kind of meditation on what infinity really means when applied to the realm of possibility. In an infinite context, every possibility becomes actual, somewhere in the infinite output, even though we can directly engage with only an infinitesimal fraction of the total possibilities. The mathematical structure of infinite possibility is genuinely strange, and the strangeness does not go away with careful analysis. It deepens, becoming more precise and more interesting as we develop the tools to think about it more carefully. There is a question about infinity that I want to address tonight because it touches the relationship between mathematics and the physical world, and because it has implications for how we should think about the various infinities we have been discussing. The question is whether infinity is real in some specific sense, or whether infinity is merely a useful mathematical fiction that does not correspond to anything in actual reality. The question is genuinely contested among philosophers and mathematicians, and the various positions on it reveal interesting features of how we should think about both mathematics and reality. Let me start with the position that infinity is not real, but is merely a mathematical fiction. This position has been held by various philosophers and mathematicians throughout history, and it has serious arguments in its favor. The basic claim is that infinity, as a concept, is useful for various mathematical purposes, but it does not correspond to anything that actually exists in the physical world. Real things, in this view, are always finite. Real quantities, real durations, real spatial extents, real numbers of objects are always finite quantities. The infinity that appears in our mathematics is a useful idealization, a limit concept that we approach in our thinking without ever actually reaching it. Mathematical infinity is a tool, not a reality. The arguments for this position are several. First, we have never observed anything genuinely infinite in the physical world. Every physical quantity we have ever measured has been finite. Every spatial extent we have ever traversed has been finite. Every duration we have ever experienced has been finite. The infinities that appear in physical theories typically indicate that the theories are breaking down, as in the singularities of general relativity that we discussed in connection with black holes. The actual physics, when it is understood properly, is presumably finite throughout, with the infinities being mathematical artifacts of our incomplete theoretical frameworks. Second, the mathematical theories of infinity, while internally consistent, generate paradoxes when applied to physical situations. The various infinity paradoxes we have been discussing, including Hilbert's Hotel and the Ross-Littlewood paradox and others, suggest that infinity does not behave coherently in the way that physical things behave. If we try to instantiate Hilbert's Hotel in the actual world, the various manipulations that the thought experiment describes would not be physically realizable. The hotel cannot actually exist, with its infinite rooms and infinite guests, in any way that would allow the rearrangements that the mathematics describes. The mathematical possibility does not translate into physical possibility, and the gap between them suggests that infinity is essentially a mathematical concept that cannot be physically realized. Third, the various theories that propose physical infinities, including infinite cosmology, infinite multiverse theories, and infinite divisibility of matter, are not directly supported by observation. They are inferred from theoretical considerations that may or may not be correct. The actual evidence we have access to is consistent with finite physical reality, with the infinities being theoretical extrapolations beyond what observation can confirm. A physical universe that is finite but very large would be observationally indistinguishable from a physical universe that is infinite, given the finite range of our observational access. So the assumption of physical infinity is, in this view, an unnecessary theoretical commitment that goes beyond what the evidence supports. These arguments have considerable weight, and the position that infinity is merely a mathematical concept rather than a physical reality has been defended by serious thinkers throughout the history of philosophy. The position is sometimes called finitism, and it has had various advocates, including some prominent mathematicians and philosophers of mathematics. Now let me turn to the opposite position, which holds that infinity is real in some genuine sense, and that the mathematical theories of infinity are tracking actual features of reality. This position has its own arguments, and they are also serious. The first argument is that mathematics has been remarkably successful in describing physical reality, and the parts of mathematics that involve infinity have been just as successful as the parts that involve finite quantities. The calculus, which is central to physics and engineering, depends fundamentally on the concept of infinity through limits, infinite sums, and infinite processes. The various physical theories that we use to describe nature, including general relativity and quantum mechanics, employ mathematical structures that involve genuine infinities. If we are to take the success of these theories as evidence about reality, then we have to take their reliance on infinity as evidence that infinity is somehow real, or at least that it is part of the genuine mathematical structure that reality manifests. The second argument is that the alternative to infinity, finitism, faces its own difficulties. If we insist that all real quantities are finite, we have to specify some maximum quantity, some upper limit beyond which nothing can exceed. But any specific upper limit seems arbitrary. Why would the maximum number of particles be one number rather than another? Why would the maximum spatial extent be one specific size rather than another? The finitist has to either accept some specific maximum, which seems arbitrary, or accept that there is no specific maximum, but that all actual quantities are below some unspecified upper bound, which is essentially the assumption that quantities can be arbitrarily large, which is essentially the concept of potential infinity. Finitism, when worked out in detail, often turns out to require some form of infinity in its formulation, even when it tries to avoid actual infinities. The third argument is that some specific features of physical reality seem to require infinity for their proper description. The continuity of space and time, if it is real, involves infinite divisibility, with each region of space containing infinitely many points. The wave functions of quantum mechanics, which describe physical systems, take values across continuous ranges that involve uncountable infinities. The mathematical structures that we use to describe physical reality consistently involve infinity in deep ways, and the success of these descriptions suggests that the involvement is not accidental. The position that infinity is somehow real has been defended by various philosophers and mathematicians, including the mathematician Kurt Gödel, who held strongly Platonist views about the reality of mathematical objects. According to this position, the mathematical universe contains genuine infinities, and the various infinities that mathematicians have discovered are real features of mathematical reality, with their own existence independent of human thought about them. Between these two positions, finitism on one side and Platonism about infinity on the other, there is a range of intermediate views that try to capture insights from both sides. Some philosophers hold that infinity is real in mathematics, but not in physics, with the physical world being finite, even though the mathematical descriptions of it employ infinite concepts. Others hold that potential infinity is real, but actual infinity is not, with quantities being able to exceed any specific bound, but not actually being completed infinite collections. Others hold that infinity is real in some specific physical contexts, but not others, with the question of when infinity applies being itself an open question that requires careful investigation. The dispute between these positions has been ongoing for a long time, and it has not been definitively resolved. The various arguments on each side have weight, and the choice between positions depends partly on prior commitments about the nature of mathematics and reality that are not themselves settled by the available evidence. What I find interesting about the dispute is what it reveals about the relationship between our mathematical descriptions and the reality those descriptions are supposed to capture. Mathematics has been remarkably successful as a tool for describing physical reality, but the specific mechanisms by which mathematical descriptions correspond to physical reality are not fully understood. The role of infinity in this correspondence is one of the deeper puzzles, with the question of whether the infinities in our mathematics correspond to anything in reality being one of the more genuinely contested issues. I want to bring in here something specific that touches on this question. The recent advances in cosmology have produced theories that seem to require physical infinity for their proper formulation. The theory of cosmic inflation, which we discussed in an earlier exploration, suggests that the inflationary process produces an infinite extent of space, with our observable universe being just one bubble in a vastly larger inflating structure. The various multiverse theories that emerge from string theory and other approaches to fundamental physics similarly involve infinite or extremely large numbers of distinct universes. If these theories are correct, then physical infinity is not just a mathematical idealization, but an actual feature of reality, with the universe extending forever in some specific sense. Whether these theories are correct is, of course, an open question. The empirical support for them is indirect, since by their nature they predict structures that we cannot directly observe. Some physicists have argued that the theories are unfalsifiable in principle and therefore not properly scientific. Others have argued that the theories make specific predictions that can be tested, even if the testing is difficult. The status of these theories, and therefore the status of the physical infinities they imply, remains contested within physics and philosophy of physics. There is another aspect of the relationship between infinity and reality that I want to address. The infinity of mathematical structures, even if it does not correspond to physical infinities, may have real consequences for how we should think about mathematical truth. If the natural numbers extend forever, with each natural number being a specific entity, then there are infinitely many true statements about specific natural numbers. The proposition that 1 + 1 = 2, the proposition that 2 + 2 = 4, the proposition that 3 + 3 = 6, and so on through the infinite sequence of natural numbers are all specific true propositions. If all these propositions are real truths, then there are infinitely many real mathematical truths, with the totality of mathematical truth being an infinite collection. This raises questions about the nature of truth itself. Are these infinitely many truths all real in some specific sense? Or is the infinity merely a manner of speaking, with only the specific finite truths that humans actually consider being genuinely real? The Platonist about mathematics says that all the truths are real, with mathematical reality containing infinitely many specific truths, whether or not any human considers them. The constructivist or formalist says that only the truths that are explicitly worked out are genuinely real, with the infinity being a feature of our formal systems rather than of any independent mathematical reality. The choice between these positions has implications for how we should think about mathematics in general and infinity in particular. I want to close this part with a thought that may seem speculative, but that I think is worth considering. The very fact that we have developed the capacity to think about infinity is itself remarkable. Our minds, which evolved in finite environments and which developed through processes that involved finite quantities of resources and time, have somehow acquired the capacity to formulate concepts that exceed any finite quantity. We can think about the natural numbers as an infinite collection. We can think about the real numbers as a larger infinite collection. We can think about hierarchies of infinities extending upward without limit. The fact that our finite minds can formulate these concepts at all is itself a strange feature of our cognitive situation, and it raises questions about how the capacity to think about infinity could have emerged in creatures whose biological history involved no direct contact with anything genuinely infinite. Various philosophers and cognitive scientists have proposed different accounts of this capacity. Some argue that our concept of infinity is essentially a generalization from our experience of large quantities, with the infinity being constructed by extending the pattern of finite quantities indefinitely. Others argue that our concept of infinity is something more fundamental, perhaps a primitive cognitive capacity that does not reduce to extension from finite experience. Still others argue that our access to infinity comes through our access to mathematical reality, with mathematical Platonism providing a framework within which finite minds can engage with infinite mathematical structures. The various accounts are not fully compatible with each other, and the question of how finite minds can grasp infinity remains genuinely open. So as you continue to drift, hold this image in your mind. The mathematical universe, populated by infinitely many infinities, with structures of vast complexity that extend in every direction far beyond any specific human exploration. Some of these structures correspond to features of physical reality in ways that allow us to use mathematics to describe the world. Others may exist only as mathematical possibilities, with no physical instantiation in the universe we inhabit. The relationship between mathematical reality and physical reality is not fully understood, with the role of infinity in that relationship being one of the deeper puzzles. We sit, as human thinkers, at a small intersection between our finite cognitive capacities and the vast mathematical structures that we have managed to articulate. The articulation is genuine in the sense that we can prove things about infinite structures and use them in various practical applications. But the deeper question of what these structures are, in some metaphysical sense, and how our access to them is possible, remains a genuinely open question. The contemplation of this question, on a quiet night like this one, is itself a kind of acknowledgement of the strange privilege of being thinking creatures who can engage with concepts that vastly exceed our direct experience, in ways that connect us to the deepest mysteries of mathematics and reality. There is a particular relationship between infinity and human thought that I want to explore tonight, and it concerns the religious and spiritual traditions that have developed across human cultures. Because infinity, before it became a precise mathematical concept, was a religious and philosophical concept, and the traditions that have engaged with infinity in religious contexts have produced some of the most interesting and sophisticated reflections on the topic. Tonight, I want to walk you through how various religious and spiritual traditions have understood infinity, what their understandings might tell us about the human relationship with the concept, and what residues of these older understandings continue to shape how we think about infinity today. Let me start with the most basic observation. Across nearly every religious tradition that has developed elaborate theological frameworks, the divine has been associated with infinity in some specific way. The pattern is striking enough to require explanation. In the Abrahamic traditions, including Judaism, Christianity, and Islam, God is typically understood as infinite in various respects. God is infinite in power, infinite in knowledge, infinite in goodness, infinite in being. The various attributes of God are characterized as being without limit, with the infinity of these attributes being one of the features that distinguishes God from creatures. Creatures are finite, with definite limits to their capacities and existence. God is infinite, with no such limits. This basic pattern, the association of the divine with infinity and the creature with finitude, has been worked out in elaborate detail by theologians across these traditions, with extensive technical vocabulary developed for discussing the various ways that divine infinity differs from the finitude of created things. The pattern extends beyond the Abrahamic traditions. In various forms of Hinduism, the divine is associated with infinity through the concept of Brahman, the ultimate reality that is understood as boundless, all-pervading, and beyond any finite description. The various deities of the Hindu pantheon are often understood as manifestations or aspects of this infinite ultimate, with the underlying reality being infinite, even when the specific manifestations have finite forms. In Buddhism, the various Buddhas and Bodhisattvas are often described as having infinite qualities, including infinite compassion, infinite wisdom, and infinite skillful means. The very nature of enlightenment is understood as transcending finite categories, with the mind of the Buddha extending beyond any specific limit. In Taoism, the Tao itself is described as inexhaustible, with the source of all things being beyond any specific characterization or limit. The consistency of this pattern across cultures that supposedly developed independently is remarkable. Why should the divine be associated with infinity so consistently across human religious traditions? The standard explanation involves several factors. First, the religious imagination tends to extend in directions that go beyond the limitations of ordinary experience. The divine, by definition, is something more than ordinary creatures, and the natural way to characterize this moreness is through the negation of limits. If creatures are finite, the divine is not finite. If creatures are limited in power, knowledge, or being, the divine is not limited in these respects. The negation of limits naturally produces the concept of infinity, with the divine emerging as the entity to which no limits apply. Second, the actual encounter with religious experience has often been described in terms that involve a sense of unboundedness. Mystics across traditions have reported experiences of merging with something vast, of losing the boundaries of the self, of encountering a presence that extends in all directions without limit. Whether these experiences are accurately described as encounters with genuine infinity, or whether they are rather encounters with very large but finite realities that exceed ordinary experience, is a question that admits of different answers. But the phenomenology of the experiences has consistently involved a sense of unboundedness that maps onto the concept of infinity, and this experiential dimension probably contributes to why infinity has been central to religious thought across cultures. Third, the religious traditions have often been responding to philosophical pressures that pushed in the direction of infinity. The various arguments for the existence of God developed in philosophical theology, including the cosmological arguments, the ontological arguments, and various other arguments, often arrive at the conclusion that there must be some entity that is infinite in some specific respect. The cosmological arguments, for instance, often argue that the chain of causes must terminate in some uncaused cause, and the uncaused cause is then characterized as having various infinite attributes that distinguish it from the contingent finite things it produces. The philosophical pressures and the religious imagination reinforce each other, with the result that infinity becomes central to the theological frameworks that emerge from this combination of pressures and imagination. I want to bring in here something specific about the medieval theological treatment of infinity, because the medieval theologians produced some of the most sophisticated reflections on the topic that have ever been developed. The theologians of the medieval Christian tradition, including figures like Anselm of Canterbury, Thomas Aquinas, and Duns Scotus, devoted enormous intellectual energy to working out the precise nature of divine infinity and how it differs from the various kinds of mathematical and physical infinity that they were aware of. Their treatments anticipate many of the distinctions that mathematicians would later develop in the rigorous analysis of infinity, though the medieval theologians were working with different conceptual tools and aiming at different goals. The medieval distinctions are worth lingering on. The theologians distinguish between several different kinds of infinity, with different theological implications for each. There was potential infinity, the kind of infinity that exists when a process can continue without limit, even though at any given moment, only a finite portion has been completed. There was actual infinity, the kind of infinity that would exist if a completed infinite quantity could exist as such. There was infinity by addition, the kind that emerges from adding more and more to a quantity without limit. There was infinity by subtraction, the kind that would emerge from dividing a quantity into smaller and smaller parts without limit. There was the infinity of magnitude, applied to extended things like space or time. There was the infinity of multitude, applied to countable collections of discrete items. There was the infinity of perfection, applied to qualitative attributes that exceed any specific limit. The medieval theologians worked through how these different kinds of infinity related to each other, which kinds were possible and which were not, and how the divine attributes related to the various kinds of infinity. Aquinas, in particular, argued that the divine is infinite in a special sense that he called infinity of essence, distinct from the various kinds of quantitative infinity that the Greek philosophers had analyzed. Divine infinity, in Aquinas' view, was not a matter of being unboundedly large in some specific dimension, but a matter of having no limits whatsoever, of being the very fullness of being itself. This kind of infinity was not commensurable with quantitative infinities, but was something different in kind, with the relationship between divine infinity and quantitative infinities being one of the deeper questions in scholastic theology. The technical apparatus developed for thinking about this question is remarkable in its sophistication, even though the modern reader has to work to understand the specific terms and distinctions being employed. The mystical traditions within these religions developed their own approaches to infinity, often complementing the more analytical theological approaches with experiential and devotional dimensions. The Jewish mystical tradition of Kabbalah developed elaborate frameworks for thinking about the relationship between the infinite divine and the finite created world, with the concept of Ein Sof, meaning without end, being central to these reflections. The Christian mystical tradition produced figures like Meister Eckhart, who wrote about the divine in terms that emphasized its infinity and the possibility of the human soul somehow uniting with this infinity through specific contemplative practices. The Islamic mystical tradition of Sufism developed its own elaborate vocabulary for the divine infinity and the human relationship with it, with various Sufi poets and theologians producing some of the most beautiful religious writing on these themes ever composed. The Hindu and Buddhist mystical traditions produce their own extensive literatures on the experiential dimensions of encountering what they understood as ultimate reality, with the unboundedness and infinity of this reality being recurring themes. I want to draw out something that I find particularly interesting about the relationship between religious infinity and mathematical infinity. The concepts have, in important respects, developed in parallel across the history of human thought. The religious traditions have been thinking about infinity in their specific theological and mystical context for thousands of years, while the mathematical traditions have been developing their own analyses of infinity over a comparable period. The two streams of reflection have sometimes interacted, with theologians drawing on mathematical concepts and mathematicians drawing on theological frameworks, but they have also developed substantially independently of each other. The interactions, when they have occurred, have sometimes been productive. Cantor, when he developed his rigorous mathematical theory of infinity in the late 19th century, was conscious of the theological dimensions of his work and engaged with theological concerns about whether the mathematical analysis of actual infinity was compatible with traditional theological views about divine uniqueness. Cantor argued that his mathematical infinities were consistent with theological infinity, with the absolute infinite being something different from any of the mathematical infinities he had analyzed. He even corresponded with Catholic theologians about these issues, and his work was influenced by theological considerations, even as it pursued purely mathematical goals. The medieval theologians, working with the conceptual tools available to them, anticipated some of the distinctions that modern mathematics would later make rigorous. The distinction between potential and actual infinity, the recognition that there could be different kinds of infinity, the awareness that infinity does not behave like ordinary quantity, were all present in some form in the medieval theological literature, even though the rigorous mathematical formulation came much later. The continuity between the medieval reflections and the modern mathematical analysis is therefore real, even though the specific modes of analysis are different. There is one more aspect of religious infinity I want to address before we close this part. The traditions have generally held that contemplating the divine infinity is itself a worthwhile spiritual practice, with the contemplation producing various effects on the contemplator that are valued within the relevant religious frameworks. The meditative practices of various traditions involve sustained attention to the unboundedness of the divine, with the practitioner attempting to allow their finite mind to engage with the infinite reality in whatever way is possible. The results of such practice are described in various ways, including the development of specific cognitive and emotional capacities, the experience of altered states of consciousness, and the eventual transformation of the practitioner in ways that are understood to bring them closer to the divine. The specific effects of contemplating infinity have been described in remarkably consistent ways across traditions. The contemplator typically experiences a sense of expansion as their ordinary cognitive boundaries seem to extend or dissolve. There is often a sense of awe as the magnitude of what is being contemplated exceeds what ordinary experience prepares one for. There is sometimes a sense of self-loss, as the boundaries of the individual self become less defined in the encounter with what is unbounded. These effects, whatever their ultimate metaphysical status, are experiential phenomena that have been reported with sufficient consistency across traditions and individuals that they probably reflect genuine features of how the human mind responds to extended contemplation of infinite concepts. The contemplation of infinity, even on a quiet night spent listening to a discussion of mathematical and physical infinities, may produce some attenuated version of these experiential effects, with the contemplator's ordinary cognitive boundaries being somewhat extended through the engagement with concepts that exceed finite limits. So as you continue to drift, hold this image in your mind. A medieval contemplative, perhaps a monk in some quiet monastery in the Christian tradition, or a Sufi practitioner in some Islamic context, or a meditator in some Buddhist or Hindu tradition, sitting in their dedicated space late at night, engaged in sustained attention to the unbounded reality that their tradition has taught them to recognize. The practitioner has spent years, perhaps decades, cultivating the capacity for this kind of attention. Their mind, through long practice, has become able to engage with concepts of unboundedness in ways that ordinary minds cannot easily achieve. They are, in the practice of this evening, doing what countless contemplatives across cultures have done across thousands of years. They are extending their finite minds in the direction of the infinite, allowing the contemplation of the unbounded to produce whatever effects it produces, participating in a long human tradition of trying to engage with what exceeds finite limits. The specific theological frameworks within which they are working may differ from the frameworks within which other contemplatives have worked. But the underlying activity, the cultivated attention to the unbounded, is recognizable across traditions. Tonight, like every night somewhere in the world, contemplatives are engaged in this kind of practice. Tonight, like every night, the human relationship with infinity is being cultivated in countless small ways across countless places by people whose names we do not know, but whose practice contributes to the long human conversation about what it means to be finite creatures who can think about what is not finite. The contemplation of this, on a quiet night like this one, is itself a small participation in that long conversation, even if you do not belong to any specific contemplative tradition. The thinking about infinity, careful and patient and extended, is itself a kind of contemplation, with its own effects on the mind that engages in it. There is one final aspect of infinity I want to explore tonight, before we move toward closing our exploration. The aspect concerns the relationship between infinity and human finitude, and what it means for finite creatures like ourselves to spend our brief existence thinking about something that exceeds any finite limit. Because there is something genuinely strange about the situation we are in. We are finite beings with finite lifespans, finite cognitive capacities, finite attention spans. We exist in finite bodies, in finite locations, during finite moments of cosmic history. And yet we have somehow developed the capacity to think about infinity, to reason about infinite quantities, to engage philosophically and mathematically with concepts that exceed any finite scope. The relationship between our finitude and our engagement with infinity is itself one of the genuinely interesting features of what it means to be the kind of creature we are. Let me start with the basic facts of our finitude, because they form the context within which our engagement with infinity has to be understood. The average human life is approximately 80 years, give or take a few decades depending on circumstances. During those years, we are conscious for some fraction of the time, with the conscious moments being further fragmented across various activities and states of attention. The total quantity of conscious experience that any individual human accumulates across a complete life is, by any reasonable measure, finite. We can put approximate numbers on it, with various calculations producing estimates of how many waking hours we typically experience, how much information we typically process, how many specific thoughts we typically have. The numbers are large by ordinary standards, but they are finite, with definite upper bounds that no individual human exceeds. Within this finite span of conscious experience, the time available for engaging with abstract concepts like infinity is itself a small fraction of the total. Most of our conscious moments are occupied with practical concerns, with attending to immediate sensory experience, with social interactions, with the ordinary activities of being embodied creatures in a physical world. The moments we devote to abstract thought, to mathematical reasoning, to philosophical reflection, are a relatively small portion of our total conscious experience. And within that portion, the moments specifically devoted to thinking about infinity are smaller still. We are, as engagers with infinity, occupying a tiny fraction of our already finite existence with a kind of thinking that very few of our conscious moments actually involve. This raises an interesting question. Why do we engage with infinity at all, given how finite we are and how disproportionate the engagement seems to our other concerns? The question can be answered at different levels. At one level, the engagement is practical. The mathematics involving infinity has turned out to be enormously useful for various purposes, including the physics that has produced our technological civilization. The calculus, with its essential dependence on infinite processes, is the foundation of the physical and engineering sciences. The various mathematical structures that involve infinity have applications across numerous fields, from economics to computer science to biology. The engagement with infinity is therefore not merely a luxury, but a productive activity that yields real practical benefits. But this practical answer does not capture the deeper dimensions of why we engage with infinity. The mathematicians and philosophers who have done the most work on infinity have not generally been motivated primarily by practical concerns. They have been motivated by curiosity, by the desire to understand, by something like an intellectual attraction to the strangeness of infinity that draws them to spend their finite time and attention on engaging with concepts that vastly exceed their own existence. The motivation is not fully captured by appeals to utility, even though utility is a real consequence of the work. Something else is going on, and the something else has to do with how the human mind responds to encountering infinite concepts. I want to suggest that part of the appeal of engaging with infinity is precisely the contrast it produces with our own finitude. When we contemplate infinity, we are encountering something that we are not. We are finite, and infinity is not finite. The contrast highlights features of our own situation that we might not otherwise recognize clearly. The contemplation of infinity is, in a sense, a way of becoming more aware of our own finitude, with the awareness producing both humility and a kind of liberation. We are humbled by the recognition of how small our individual existence is compared to the infinite quantities we can think about. We are also liberated, in some sense, from being trapped in purely finite concerns, because the very capacity to think about infinity expands the cognitive space within which we operate. There is something almost paradoxical about this. Finite creatures like ourselves cannot actually contain infinite quantities within our minds. We cannot directly experience or visualize or fully grasp infinity in the way we can grasp finite things. The infinity remains beyond our complete comprehension, even as we develop tools and concepts for analyzing it. But the partial engagement we are capable of, the formal manipulation of infinite concepts, the proof of theorems about infinite structures, the reasoning about implications of infinite assumptions, is itself a remarkable cognitive activity. We are doing something that finite creatures might not have been expected to be able to do. We are working with concepts that exceed our cognitive capacity in some respects, while still managing to make rigorous progress on them through the development of formal tools that compensate for the limitations of our intuitive grasp. I want to bring in here something about the relationship between time and our engagement with infinity. We have been thinking about infinity as a species for thousands of years. The various traditions of philosophical and mathematical reflection on infinity have been developed by countless thinkers across many centuries, each contributing some specific increment to the accumulated understanding. No individual thinker has produced more than a small portion of what we now know about infinity. The mathematical theory of infinity that we have today is the product of work by Cantor, by his predecessors who prepared the ground for his contributions, by his successors who extended his work, by countless others who contributed specific insights or refinements. The understanding of infinity is a collective achievement of human thought accumulated across generations, with the current state of our understanding being the cumulative result of an enormous quantity of patient effort by many individual minds. This is itself a striking feature of how we engage with infinity. No individual mind has the capacity to understand infinity in its full mathematical depth from scratch, starting from no prior knowledge. The understanding requires building on the work of previous thinkers, learning the technical vocabulary and the formal tools that have been developed over centuries, and adding one's own contribution to the ongoing project. The engagement with infinity is therefore inherently collaborative and historical, with our finite individual minds being able to participate in something larger than ourselves through our membership in a tradition of inquiry that extends across generations. This pattern is not unique to infinity, of course. Most significant intellectual achievements are similarly collaborative and historical, with current understanding being built on the cumulative work of previous thinkers. But the engagement with infinity has a particular intensity to this pattern, because the topic itself requires the development of concepts and tools that no individual could plausibly produce alone. The infinity that we can think about today is, in a real sense, larger than the infinity that any specific individual thinker could grasp without the support of the tradition. The traditions of mathematical and philosophical thought have, through their cumulative work, expanded the human capacity to think about infinity beyond what would otherwise be available. There is a deeper reflection that follows from this. We are not just finite individuals who happen to think about infinity. We are participants in a long human project of engaging with infinity, with our individual contributions being part of a larger pattern that extends back through history and forward into the future. Our finite lives connect with this larger project, with each individual life adding some small increment to the accumulated understanding, while drawing on the much larger inheritance from previous generations. The relationship between our individual finitude and our participation in this larger project is one of the more interesting features of what it means to be a thinking creature engaged with infinity. I want to bring in here a thought that I find particularly poignant. The tradition of human reflection on infinity has been carried by individual minds, each of which has been finite. Cantor, who did so much to transform our mathematical understanding of infinity, lived a finite life of approximately 73 years and died in 1918. His specific contribution to the understanding of infinity was made within the constraints of his finite existence. Aquinas, who worked out elaborate theological frameworks for thinking about divine infinity, lived approximately 49 years and died in 1274. The medieval theologians who developed sophisticated technical vocabularies for various kinds of infinity all lived finite lives, with their contributions emerging from those finite existences. The various thinkers across all the traditions of reflection on infinity have all been finite individuals, working within the constraints of their finite existences, contributing what they could before their finite time ended. The work continues in subsequent generations, with new finite individuals taking up the threads that the previous generation has provided. This is itself a remarkable pattern. Each generation of thinkers about infinity inherits the work of previous generations, develops it in some specific direction, and passes it on to subsequent generations. The tradition extends across centuries through this process of intergenerational transmission, with the cumulative understanding being something that no individual member of the tradition could have produced alone. The relationship between individual finitude and tradition continuity is fundamental to how the engagement with infinity has actually proceeded across human history. There is one more aspect of our finitude in relation to infinity that I want to address. The engagement with infinity, while it cannot eliminate our finitude, can change our relationship to it. The contemplation of infinite quantities tends to produce, in those who engage in it sustainedly, a particular orientation toward finite things. The orientation is not exactly indifference to finite concerns, but it is a kind of contextualization of those concerns within a larger frame. The various ambitions and worries and projects that occupy finite human lives appear, when seen against the background of infinite quantities, as the small and specific things that they are. They do not become unimportant, but they become located within a larger context that helps to put them in proportion. This effect has been noticed by various contemplatives and philosophers across traditions. The sustained engagement with infinity produces, over time, a kind of equanimity about ordinary finite matters, with the practitioner becoming less captive to the various anxieties and ambitions that dominate ordinary life. The effect is not automatic, and it requires sustained practice rather than occasional reflection. But it is real, and it has been described with sufficient consistency across traditions to suggest that it reflects a genuine feature of how the human mind responds to extended engagement with infinite concepts. I am not suggesting that everyone should pursue contemplative engagement with infinity as a path to equanimity. The path is demanding, and it does not suit everyone. But the recognition that such engagement can produce real effects on those who pursue it is worth noting, because it suggests that thinking about infinity is not just an abstract intellectual activity, but something that can actually change how we relate to our own finitude. The change is not magical, and it does not eliminate our finite limitations, but it can shift how those limitations feel, with the contemplation of the infinite providing a context within which the finite can be experienced more lightly and with less anxiety. So as you continue to drift, hold this image in your mind. A long line of thinkers extending back through human history, each one finite, each one having lived a specific finite life, each one having contributed something specific to the human engagement with infinity. The line includes mathematicians and philosophers and theologians and mystics and ordinary people who have spent quiet evenings thinking about the unbounded nature of various aspects of reality. The line extends from the present moment back through the centuries, with each generation building on the work of previous generations, with each individual contribution adding to the accumulated understanding. The line continues forward into the future, with new generations of thinkers taking up the threads that the present generation provides, extending the engagement with infinity into directions we cannot now foresee. You and I, sitting in our brief moments of conscious existence, are participants in this long line. Our specific contribution to the engagement with infinity may be small, perhaps just the contemplation of these specific ideas during this specific quiet evening. But our participation is real, even if its effects are modest. The long line of thinkers connects us to all the previous humans who have engaged with infinity, and through us to all the future humans who will continue the engagement after we are gone. Tonight, like every night, somewhere in the world, someone is engaging with infinity in some specific way. Tonight, like every night, the long human conversation about the unbounded nature of various aspects of reality is being carried forward by individuals whose names we do not know, but whose participation contributes to the larger pattern. The pattern continues. The conversation continues. The engagement with infinity continues across the centuries and across the lives of countless finite individuals who have somehow developed the capacity to think about what exceeds finite limits. We come now to the closing part of our long exploration, and I want to use it to draw together what we have been discovering across these many hours, and to leave you with the right kind of questions to carry into the sleep that is now, I hope, very close. Because the cumulative weight of everything we have examined tonight points toward a picture of infinity that is far stranger and more genuinely interesting than any casual encounter with the concept would suggest, and the picture has implications for how we should think about ourselves and our relationship to the larger reality within which we exist. What have we actually been doing across these many hours of patient examination? We have been walking carefully through the strange concept of infinity, examining its various aspects from multiple angles. We began with the basic observation that infinity, despite its apparent simplicity, turns out to be a genuinely complex concept that does not reduce to any simple intuitive description. We saw that the mathematical analysis of infinity, developed primarily by Cantor in the late 19th century, demonstrated that there are different sizes of infinity, with some infinities being strictly larger than others in a precise mathematical sense. We considered Hilbert's Hotel and other thought experiments that reveal the strange properties of infinite collections, including the way that adding to or subtracting from infinite collections can leave them with the same cardinal size as before. We examined the question of whether the universe itself is infinite, with the various implications that cosmic infinity would have for the nature of reality and our place within it. We addressed the various paradoxes that infinity produces when applied to physical situations, including the unsettling implications of infinite probability in cosmic contexts. We considered the relationship between infinity and time, with the open questions about whether the past or the future are temporally infinite. We explored the role of infinity in religious and spiritual traditions, with the consistent association of the divine with various forms of infinity across cultures that supposedly developed independently. We addressed the deep philosophical question of whether infinity is real or merely a useful mathematical fiction, with the various positions on this question revealing interesting features of how we should think about the relationship between mathematics and reality. And we considered the strange situation of finite creatures like ourselves engaging with infinite concepts, with the long human tradition of reflection on infinity being carried forward by individual finite minds across many centuries. Each of these topics, taken individually, is interesting. Taken together, they form a picture that I want to articulate carefully now. The picture is that infinity is not just a mathematical curiosity or a poetic flourish. It is a concept that touches the deepest issues in mathematics, physics, philosophy, and religion, and it forces us to confront the limits of our intuitions while simultaneously expanding what we can think about. The engagement with infinity is one of the most genuinely demanding intellectual activities that humans have ever undertaken. And it continues to produce new insights and new puzzles even after centuries of careful work. This recognition has implications that I think are worth sitting with carefully. The first implication is that the universe we inhabit, regardless of whether it is literally infinite in physical terms, contains structures and possibilities that exceed any finite description. The mathematical realities that we have discovered through our analysis of infinity are part of the fabric of what we know about reality, with their patterns and relationships being as objective and as real as any other features of mathematics. We exist as finite creatures within a larger context that includes infinite mathematical structures, and our access to those structures, however partial, is one of the genuinely remarkable features of our cognitive situation. The second implication is that the categories of common sense, while they work well for ordinary finite contexts, do not extend cleanly into infinite domains. The various paradoxes we have examined reveal that our intuitions about quantity, about probability, about size and proportion all break down when applied to infinite collections. The careful analysis of these breakdowns has been one of the major achievements of mathematical and philosophical thought, with the resulting frameworks providing tools for thinking about infinity that go beyond what intuition alone could provide. We have developed, as a species, the capacity to think about quantities that no individual mind could intuitively grasp, and the development is one of the more impressive collective achievements of human thought. The third implication concerns the relationship between finitude and infinity. We are finite creatures who can think about infinity. This is itself remarkable, and it means that our cognitive situation is more interesting than the simple description of us as finite would suggest. We extend, through our mathematical and philosophical reflection, beyond the strict limits of our finite existence, engaging with concepts and structures that exceed any specific finite quantity. The engagement does not eliminate our finitude, but it does change what finitude means for creatures like us. We are finite in some respects, but our cognitive reach is not strictly limited to finite quantities, and this asymmetry is part of what makes us the kind of creature we are. The fourth implication, and the one I want to leave you with, concerns the practical effect of contemplating infinity on how we live our finite lives. The sustained engagement with infinity, when it is undertaken seriously, tends to produce a particular orientation toward our specific finite circumstances. The orientation is not exactly indifference, but it is a kind of contextualization, with the various concerns of finite life being placed within a larger frame that helps to give them their proper proportion. The contemplation of infinity does not solve our finite problems, but it can change how we relate to them, providing a context within which the finite can be experienced with less of the anxiety and grasping that often characterize our engagement with finite matters. There is something almost spiritual about this when you sit with it carefully, although I do not want to push the language too far in any specific direction. The traditional contemplative practices that have engaged with infinity have generally claimed that such engagement produces real effects on the practitioner, with the cumulative practice transforming how the practitioner experiences ordinary finite life. The transformation is not magical, and it does not require any specific religious commitment. It seems to be a genuine cognitive and emotional effect of sustained attention to concepts that exceed finite limits, with the attention itself producing something like an expansion of cognitive space that persists beyond the specific moments of contemplation. There is one final thought I want to leave you with as we close this exploration. The concept of infinity is not finished. Mathematics continues to develop new tools for analyzing infinity, with new structures being discovered and new relationships being established. Philosophy continues to wrestle with the implications of infinity for our understanding of reality, with the various positions being refined and new positions being developed. Physics continues to explore whether infinity is a literal feature of the physical universe, with the cosmological and theoretical work being ongoing. The engagement with infinity is a project that extends across human history, and it is not complete. New insights are still being developed, and new puzzles are still being identified. You may live to see significant developments in our understanding of infinity, with new tools and new perspectives changing how we think about questions that currently seem settled or that currently seem hopeless. The story of human engagement with infinity is itself, in a sense, an ongoing story that will continue to be written by future generations of thinkers. If you have found this exploration valuable, if the patient walk through the strange territory of infinity has given you something to carry with you as you finally drift off, please consider letting me know in the comments below. Tell me what struck you most, what questions you would like to explore further, what other deep mysteries you would like to spend a long quiet night thinking about. Subscribe to Sleepy Tin Foil Hat if the channel is the kind of thing you want more of, because the channel exists for the audience that wants this slow, careful kind of thinking. And the audience tells the algorithm we are here through the small acts of comment and subscription. The community of careful nighttime thinkers is scattered across many time zones and many lives. And the way we find each other and keep this work going is through these small signals. Sleep well. Let yourself go gently. The infinity we have been discussing tonight will still be there in the morning, in whatever sense it is there at all. The mathematical structures will continue to exist, in whatever sense mathematical structures exist. The cosmological possibilities will continue to be possibilities, with the actual situation being what it is, regardless of whether we are awake to think about it. The long human tradition of reflection on infinity will continue, with new contributions being made by other thinkers in other places while you sleep. The continuation does not depend on your specific attention or mine. The structures and relationships and possibilities continue, in their own way, across all the moments of our individual existence. We are brief participants in the engagement, contributing what we can during our finite time, then handing the engagement over to those who come after us. Tonight, like every night, you are about to surrender consciousness for some hours of unconsciousness. The infinity that has occupied our attention tonight will remain, in whatever sense it remains, while you sleep. And in the morning, when you wake, the infinity will still be there, as it has been there all along, available for further reflection by those who wish to pursue it. The pattern continues. The contemplation continues. The strange and remarkable engagement of finite creatures with infinite concepts continues. Across the centuries and across the lives of countless thinkers who have somehow developed the capacity to think about what exceeds finite limits. You have participated in this engagement tonight. You may continue to participate in it tomorrow, or you may turn your attention to other matters, returning to infinity at some other time when the mood and the moment again align. Either way, the engagement remains available, waiting for whoever wishes to pursue it, in the patient way that it has waited for all the previous generations of thinkers who have given it their finite time and attention.